technical talk jointly hosted by the Institution of Mechanical Engineers and Thai UK North. My name is Ram Shankar. I am the Honorary Secretary of the Greater Manchester Division of the IMechE, and I'm also the President of Thai UK North. In this double capacity, it gives me double the pleasure to welcome you all to this evening's lecture. Um, our speaker for today is Tej Chadeesingh from Teva Hydrogen Electric Trucks. And Tej is an MEng Mechanical Engineering graduate from the University of Birmingham, who spent all his working career helping make hydrogen electric trucks a reality with Teva Hydrogen Electric Trucks. His responsibilities have included integrating one of the first hydrogen fuel cell trucks to drive on the UK roads and developing the compressed hydrogen storage system on Teva's upcoming 7.5-ton hydrogen electric truck. When not helping to drive the introduction of this cutting-edge technology to the industry, Tej is an avid handball and football player, both of which he says are best enjoyed on the beach outside his old address in Montego Bay, Jamaica. Now, before I hand the floor over to Tej, a couple of house rules today, please. If everybody who is attending can please switch off your microphones and cameras, that'll help us do the lecture smoothly. And before anything else, without further ado, I am happy to present to you Tej Chadeesingh from Teva. Tej, take it over, please. The floor is yours.
Well, good evening, everyone, and as Ram said, yeah, good morning and good afternoon to anyone joining from other time zones. I'm just going to share the presentation for you now. So hopefully that's all up for you now. Just Ram, if you can just confirm that for me before I go any further.
That looks good, Tej. I can see it. Yeah.
Okay. Well, then without further ado, I will get into it. So first of all, thank you very much to Ram and the IMechE and Thai for this opportunity. It'll be one of my first times presenting at something like this. So it really is a pleasure. And it's also encouraging to see so many people in attendance on the call interested in hydrogen electric trucks and what we Teva are doing. Ram, thank you for that introduction to myself. It was very nice. But yes, as you say, I've had a master's degree in mechanical engineering at the University of Birmingham, and my job history has been rather short, spending all of my career making hydrogen trucks a reality. And I've been doing that as part of Teva's REX or range extender team, which means we've been introducing hydrogen fuel cell vehicle prototypes and, as Ram said, developing the hydrogen storage system. Hopefully you'll learn a bit more about all of this during the course of the presentation. You'll also learn a lot about Teva, I hope, getting into what our dual energy product is, why we've designed it the way we have, and the challenges of building it, plus what we're calling the balancing act, the balancing between electric and hydrogen as power sources for HGVs. We should hopefully have some time at the end for you to ask some questions. So while this will be a great chance for you to learn about Teva and the work we've been doing, I'm also very curious to hear the opinions of yourselves and your thoughts, as you know, a lot of the questions we're talking about today, there are no accepted correct answers. So I'm very interested to hear your thoughts.
On the matter of questions, may I just interrupt you? I've just put a note on the chat box for everybody to type your questions in the chat box, and we'll ask them in the order in which we get them at the end after Tej has finished his lecture. Thanks, Tej. Thank you for that.
No problem. Yeah, please, as I say, very interested to hear your guys' questions at the end. So please do. So yeah, first of all, first question, I think, because I imagine for some of you on the call, Teva will be a new name to you. So I would like to explain just quickly about who Teva are. So it shouldn't surprise you, as a company making zero emission vehicles, we are mission led. That is our mission there. We do technology because it matters and makes a difference to humanity. And that makes a difference to humanity really does mean something to us. We are a young team at Teva. Myself, probably a good example of this. But I think that mission is something that really resonates with people, especially amongst the younger generation. And I also would like to draw attention to that tagline we have below there as well: transporting everything for everyone. So for now, while we are making medium duty trucks, you know, we do see that this technology is something that could be transferred to other industries. And that's a big part actually of how Teva got started, which leads me neatly onto the next slide, which is a whistle stop tour of the history of Teva. So Teva's journey. Our CEO and founder, Asher Bennett, was an Israeli submarine captain, right? He captained electric submarines that had diesel generators. Their electric powertrains meant that the sub could operate in near silence when it needed to, and the diesel generator was there to give it range. As serial entrepreneur, he formed Teva, which is the Hebrew word for nature, to apply this idea to trucks. Teva has actually been around for over 10 years now, which is a lot longer than some of the other electric vehicle startups we're often compared to. Our first product that the company spent its first 5 to 7 years building towards are the UPS trucks I've just put on the screen for you now. These were Mercedes UPS vans converted to run with an electric motor and featured a diesel engine used as a range extender, not unlike the submarines that Asher used to work on. So these 15 vehicles have been out on the road for several years now. They've achieved more than 400,000 kilometers of real-world experience. And if you've ever been in Tamworth or Southampton, you might have seen them driving around. Our next step to go from there was to move from doing vehicle conversions to making a chassis cab platform that could be used for a range of purposes, whether you need a flatbed, a box body, refrigeration, drop side, curtain side. We wanted to have a Teva product that could be used by all manner of customers. So what you can see on the screen there is our 7.5-ton battery electric vehicle. So this is our first product, is a battery electric vehicle with no range extender, and that has just secured European whole vehicle type approval, which obviously is a massive landmark for us and means we can sell our vehicles to our customers. And this will soon be followed by the subject of this talk, which you can see in the top right there, which is our dual energy product. And what this is a battery electric vehicle with a hydrogen fuel cell used as a range extender. You can see the telltale column of hydrogen cylinders behind the cab, which incidentally is also how I met Ram for the first time. We obviously have moved away from doing diesel range extenders, which are as simple as they sound. They are a diesel engine used as a generator. We moved away from these because although they do significantly lower emissions, what customers and governments are looking for now is zero emissions, not just reduce. The bottom left is our main headquarters in Tilbury, Essex, just outside of London. We moved into this facility in October 2021, and it is already a fully functioning production line, and at full capacity on a double shift could produce 3,000 trucks a year. This next image is the first truck to come off our production line and be delivered to our first customer, obviously as another massive milestone that we're very proud of. And the final image I'm putting on the screen for you there is our production line as it was earlier today, which is a picture I took of the production line in full swing. On the next slide, I have a video, which is just a couple of minutes, and I put it in there just to give you an introduction for our products. And I think it explains our dual energy product better than I ever could just with words. So please have a look. Okay, so hopefully you were able to ignore some of the more egregious parts of marketing flair in there, but hopefully you were able to see visually the relationship between the hydrogen fuel cell and the battery in our dual energy product. And that's really what I was trying to get across to you from that. And you can see up here up on the screen is our current range of products. The 7.5-ton battery electric product with its range of 227 kilometers. That's what we have the type approval for. That's what you can go out and buy now, and hopefully we'll be seeing on roads very quickly. And then coming a little bit further in the future is our dual energy products. First in the 7.5-ton, where it has nearly double the range of its battery only counterpart. And then we're also planning on looking at a 19-ton rigid body as well. I mentioned briefly earlier our history of UPS and the real world verification of our systems we have under our belt. But I think it's also important to mention here around an often forgotten part is the driver experience benefits of driving an electric vehicle. If you can compare spending 8 hours behind the wheel of a battery electric vehicle compared to sitting on top of a diesel engine with all its fumes, vibrations, and noise, it's a massive difference. And it's also something I learned when doing my truck license last year is just how hard navigating inner city junctions and roundabouts in a combustion engine truck can be. If any of you have ever done it, you put your foot down and the truck, it goes nowhere. So the acceleration is so slow, you end up either waiting for several minutes at every roundabout, or in my case, perhaps on my test, cutting people off. Um, so we're not making racing trucks, but the higher torque of the electric motors does mean we get off the line very quickly, and it is something for drivers to enjoy, as well as obviously the effects of regenerative braking, which means you can often drive with just one foot. And hopefully just wrapping up some information about Teva. This is our production facility. The idea behind this being small, low capex facilities can be set up quickly and close to the markets we're looking to sell in. And one final piece of information just to ram it home for you. So we have our whole vehicle type approval was achieved earlier this month, and the vehicles will be going over to customers for demos and into sales very soon as well. And we're also last week became the first British manufacturer of a small truck to be eligible for the government's plug-in grant, which it gives customers a £16,000 discount on their purchase, which obviously being an electric truck, we know our upfront cost is always going to be more expensive than our diesel equivalents. So any help we can get like that really, really does go a long way. So now hopefully you know a bit more about Teva, and you can let me get into the reasoning behind some of the decisions we've made and the motivations behind the conclusions we've come to. So, the problem. If we look at CO2 emissions globally, nearly a fifth of them come from transportation. That obviously is a massive problem. And when we start breaking that down even further, you see that a lot of these emissions are coming from trucks, medium and heavy duty trucks, 22%. Most cars have an extremely short average daily drive, which makes them fairly straightforward to electrify. First of all, you don't need to have much energy to begin with. Payload is not so much of a concern. And if you're someone who drives to work and you can charge your car at work, or you come home to your driveway and you can charge at your driveway, I think most people agree that electrifying cars is not really so much of a challenge. The challenges are perhaps more around sourcing of components and the raw materials required to make batteries than they are around the concept itself. You can also see buses make up 7% of transportation emissions. Buses have extremely consistent drive cycles, which makes converting them a lot easier. You know exactly how much energy a bus is going to use on any given day, and it doesn't tend to vary very much. They also can have relatively low payloads compared to some truck operations, but really it's the variance that really provides an issue for electrifying or decarbonizing in some form uh, medium and heavy duty trucks. Now, this variance can come from all manner of different reasons. You can have obviously varying routes, which is what we highlight that a bus or a car typically doesn't have. We can have variances in payloads. Maybe you're carrying crisps one day and bricks the next day. Auxiliary loads like fridges. On a warm day, the load from your fridge is going to be extremely high compared to on a colder day, We can also look at driver behavior as another thing we're able to highlight. We can highlight drivers that drive more efficiently. Obviously, the classic traffic, road closures can have a big effect, and weather conditions can also affect, obviously, your grip on the road, which also can have a massive impact on how much energy your vehicle is using per day. And to hopefully sort of express that, what I've got on the bottom right for you is the amount of energy used per day by 5 of our different UPS trucks in service. And you can see just how much energy can vary from day to day. So this is where you have a big problem, because you might have a truck that is good for, even if it's good for 99% of the days. If your car didn't take you to work one day out of 100, you drive that car. And it's even more serious for trucks, which are workhorses that are valued on their uptime. So what is our solution? So we try and take the balance between battery and hydrogen as fuel sources for a vehicle. So we all know that battery electric vehicles are very efficient, and when you have sufficient infrastructure to charge them, they can be ideal. For cars, this is getting in a pretty good place. More and more every single day, there are more EV charging points. EV charging infrastructure for HGVs is nowhere near as prevalent as it is for cars. I can speak from personal experience of taking Teva trucks. We're parking across several parking spaces in a supermarket, just trying to get to the charger, or maybe we're waiting at a service station because the infrastructure is not there for HGVs. And when you need to travel long distances and carry larger payloads, batteries can be a problem. We've highlighted here that a 700 kilogram battery can deliver around between 80 and 90 kilowatt hours of energy. A hydrogen cylinder that does the same thing can weigh 100 kilos. And when you consider as well that these hydrogen tanks can also be refueled in times comparable to diesel tanks, it really does start to question, okay, well, how do we make this balance work? Because we know that hydrogen is more expensive, it's harder to get hold of, but you might need it to take your vehicle to achieve what you want it to achieve. So we have what we call the balancing act and the justification for our dual energy product. Now, this bell curve here is based on some research we've done. And basically what it's trying to show is that battery electric trucks, including our own 7.5-ton product, do have a place. There are many operators who run routes that never exceed more than 100 miles. A FedEx employee in Manhattan, he might cover less than 10 miles a day delivering packages. Now, like all vehicles, this should be decarbonized. However, this vehicle's annual emissions are going to be minuscule compared to one that covers 200 miles in a day. And to make a difference to climate change, we need to decarbonize the vehicles carrying heavier loads over longer distances, not the vehicles doing shorter journeys. And the benefits of using hydrogen fuel cell as a range extender, which is what we try and show at the bottom here, with the orange section of the vehicle's total energy being the battery and the white being the hydrogen. We say that, okay, well, we almost always use all our battery and we only sometimes use the hydrogen. And what this means is if you go on a day you don't drive as far, you can use as much of the cheap electricity as possible. But on a day when you need to go further, you've got the hydrogen to take you there. So if there was just one slide or a couple of slides that I could show you today, it would be this one and the next one. So this really is what we call the case for our dual energy product. And I will say that this dual energy product is something that Teva is fairly unique in doing. Most of the other people in this space fall into two of the categories I've listed here as the hydrogen and the BEV. So if we take the diesel truck as a baseline, because this is the problem here, this is what we're trying to get rid of. We know that diesel products can transport big payloads and they can take them long distances. However, we all know the damage they do to the environment. They are cheap to purchase, but especially in recent years, they've become increasingly expensive to fuel. The total cost of ownership of a diesel truck might be more than 75% the fuel you use to refuel it with. And that's before you consider costs from taxes and the ever increasingly prevalent zero emission zones. Everyone knows about London's zero emission zone, but you're seeing them cropping up now in Bristol, in Birmingham, in Bath, Oxford, many other cities. These These zones are not going away anytime soon. They're only going to become more prevalent. And obviously, if you're operating a diesel truck, this can be a killer for your business. Now, if I take you down to the next item on the chart, is a full hydrogen truck. That is one that you wouldn't plug in to charge, unlike ours, which needs to be charged and refueled with hydrogen. To be clear, all hydrogen vehicles will have some battery of some size, all hydrogen fuel cell vehicles, that is. This battery allows you to take advantage of regenerative braking and also allows you to cover transient loads. Now, the problem with full hydrogen vehicles is they are extremely expensive to produce. You have to have an extremely powerful fuel cell to meet gradability requirements and many hydrogen cylinders to store all of the required hydrogen you're going to need. That hydrogen fuel is also, for the moment, still more expensive than diesel. Now, it should be said that the cost of powerful hydrogen fuel cells and the cost of hydrogen fuel, it will decrease, and it will decrease faster than the price of diesel is going to decrease, and it will decrease faster than the price of electricity is going to decrease. But for now, this is a very expensive product. Then we have battery electric vehicles. That's the next point on the slide. And for the same payload, which is what the restriction we put on this here, because often in the heavy duty truck world, payload is the limiting factor. So we've put, so for the same payload, our battery electric vehicle is capable of a much shorter distance. Now, this obviously means that for some customers, the vehicle is unsuitable. However, we know it's good for the planet. Their purchase cost is higher, but their operational costs are way, way lower. And that's where there really is an argument for a short range diesel vehicle, a diesel vehicle that only does a short range, especially if it's hitting like 100 miles close to the limit of the battery electric vehicle every day. That's an easy switch to make to a battery electric vehicle. The problem is that there aren't that many people existing in that space. Most customers need a product that can go further and can carry heavier loads further. So this is where our dual energy product comes in. We have still a quite excellent range. It's not as high as diesel and it's not as high as you could achieve with a full hydrogen vehicle, but it's useful for all but the most extreme drive use cases. Our purchase costs are high, but not as high as like a full hydrogen vehicle because our fuel cell can be much lower power. This makes it cheaper, it makes it lighter, and we can also use it at its most efficient point because we can use our strategy to only charge the batteries when we need it. So we have a system called PREMS, which is our Predictive Range Extender Management System. And what this allows us to do is look at a driver's route and try and calculate how much energy he's going to need to make it back to his depot. And this is all based around back to depot trucks, which are a large percentage of the market, especially at 7.5 ton. So we know our purchase cost is going to be high, but our operational costs are quite good because we're not buying hydrogen as much as a full hydrogen truck would be. We are using hydrogen only when we need it. Now, hopefully this slide helps get that point across even more. There's an expression, horses for courses, which I particularly like for explaining this. And I've got these 3 theoretical customers here. Now, customer number 1, he delivers bread in central London. We often use bread as an example of something that's lightweight, but has a large volume, so you need a truck. Another good one is toilet paper, tissue boxes. You can think of some other examples, I'm sure. So they have their set payload of 2 tons and they need to travel 80 miles a day on their route that never changes. Here, a battery electric product is the ideal choice. Because you don't need to travel so far, the amount of batteries you require don't make payload an issue. You have low TCO from a low fuel cost and no emissions charges, etc. Now, customer 2 is where we see a much bigger chunk of the market. This is much more typical in the product that people need. So this customer, they transport cloves. It doesn't really matter what it is. It typically weighs 2 tons. Most days they drive 120 miles from London to Birmingham, but once a week they have to drive 250 miles to Liverpool. So what we have here, and this is where I'll explain a bit more about our dual energy truck. We have an 112 kilowatt hour battery and 2 5-kilo cylinders of hydrogen that add another 160 kilowatt hours. This gives the vehicle a range of more than 270 miles. Now, a battery big enough to cover this distance would leave you with very little payload. So it'd be a third of what the mixed hydrogen and battery electric product is. So when you actually look at the miles and look at the customer's drive cycle, less than 20% of the miles they drive per week are on hydrogen. Plus, you're using the hydrogen fuel cell as a range extender, it keeps the capex of the fuel cell system low, and it leads you to overall TCO. You've still got no emissions charges, etc. And then we get on to customer number 3, who transports bricks that regularly weigh 3 tons. Every day he drives 400 miles. Here, you just have to concede that at the moment, there's no obvious 7.5 ton zero emissions choice. You need a massive amount of energy every single day. Only a diesel vehicle or a full hydrogen fuel cell electric vehicle would have the required energy density. The diesel vehicle pollutes, it incurs emissions charges, but even that, it would probably still be cheaper than running a full hydrogen fuel cell electric vehicle. And then what I've done in the bottom right there is I've overlaid these 3 customers we're imagining with the bell curve I showed you earlier, which shows how the battery electric vehicle captures one of the first little chunk of the market. The dual energy product we see as covering most of the market, only unsuitable for the most extreme drive cycles. So just to tell you a little bit more detail about the dual energy product, here it is up on the screen here. We've highlighted some of the key points. So if I go around clockwise, the first thing we have is our e-motor. So the twin motor and single speed gearbox is all within the same casing. So these motors are 100 kilowatts each and placed in series. The inverters, there's one per motor, is an electronic device capable of changing the frequency of the wave to change the speed of the motor. So these are switch reluctance motors, which is a technology that hasn't often been applied to electric vehicle motors. It's something we've done with a collaboration with a company called AEM up in Newcastle. These also means they have no rare earth metals, which is another key selling point. Those motors which use a permanent magnet often use rare earth metals. I'm sure you're probably aware of it, but these switch reluctance motors have a stator with poles that are not permanent magnets, but electromagnets that are energized in a certain sequence. Now, controlling this can be extremely difficult, but nowadays, thanks to power electronics advancements, it's something that's possible. So that's what we've been able to develop for our vehicle. Moving further around, we've got our hydrogen range extender system, which obviously is what we've been talking about. There's the black box underneath the cab, sits in what used to be the engine bay as the hydrogen fuel cell. And then you can see there the frame of the hydrogen fuel cell, hydrogen cylinders, sorry, and also some other parts for the hydrogen fuel cell's cooling loop. I mentioned earlier about our predictive range extended management system, how that controls the relationship between the batteries and the hydrogen fuel cell, as well as some of the other embedded operating systems and controls you'd expect on a vehicle like this. We also have our batteries and our battery management system. Its main function is to balance the state of charge of the individual cells in the modules, and these modules are clustered together to form the battery packs, which is all something we do in-house at Teva. And those are those grey rectangles that we affectionately call our sarcophagus batteries. These also are lithium iron phosphate, which means they have no cobalt in. So again, we have an advantage here where we're not relying on materials that are sort of suspect, at least the best thing you can say. Even people who claim to be sourcing them from ethical sources, it's a struggle to know where they come from. So not using rare earth metals and cobalt is important to become, first of all, resilient against stress supply chains, because we all have heard the stories about struggles of building electric vehicles. Everyone's getting after the same natural resources, but also helps to, reduce the costs and also obviously the human rights implications as well. It feeds back to what I spoke about earlier in making a difference to humanity. We want our vehicle to make a difference to humanity in all aspects of designing and building it. Next section I've called the infrastructure challenge. The first thing anyone says when we talk about building a hydrogen vehicle is, where am I going to get the hydrogen from? And again, it's something customers are worried about. It's maybe, I don't know if it's something people on this call are interested in, but I feel it's would be improper of me not to mention it. There's so many benefits around what we can do with hydrogen production and how it compares to delivering electric charging on the scale that we would need to for HGVs. The big energy companies see hydrogen as a future because it is similar to what we already exist with in our current world. Electric charging has already caused a change in behavior for so many people. This idea of driving a long distance and just stopping for 5 minutes to refill with petrol, that mindset has to go. Maybe not for cars if we get super powerful charging in service stations and so on, but for trucks, the energy required is just so high that even with 150 megawatt charging, it's going to be tough to make that a reality. Hydrogen can be produced on site in various locations and then transported where it's need to and dispensed in refueling stations that don't look dissimilar to what already exists. And that's before we already get into that most customers will have on-site diesel refueling for their trucks. And again, this is something we can accomplish fairly easily with a series of partners and have H2 delivered at their depot. This is not something you can necessarily do with electric charging. We have seen in the past customers who struggle with having enough electric capacity to recharge all of their trucks at their location. It can kind of come down to a lottery of what is the actual electrical infrastructure near your site. We have had people that have been told that you need to install a new substation just to run your electric charging for your trucks. And that's in the quantities we're talking about now. As demand gets even higher, we're going to struggle even more. I heard one of the chief engineers at IMechE talking about this problem. He said in Milan in the summer, every night when people turn their air conditioning on, the power cuts out because they can't cope with that surge in demand. Now imagine charging 100 electric trucks at the same time. There really is a problem regarding the infrastructure that potentially hydrogen would help avoid. And what we're looking to do with our electric infrastructure is have a battery size such that the demand for electric charging isn't ridiculous. And a 22 kilowatt charger run off of a 3-phase electrical supply can easily charge your truck. The product development, this is the real juice of what I was hoping to get into. What have we done and what's next? Some of you in the automotive industry will hopefully be familiar with a graph that looks a bit like this, the V diagram. So we're just trying to show that our battery electric vehicle, it's close to being ready to go. It's almost basically into customer hands. That's where we are. It's almost done. We're at the cusp of it. The dual energy product, we've gone through most of the design plays. We just need to go through those loops of redesigning, testing the product as a whole, getting the product into customer hands, and seeing their feedback and integrating that into the finished product. But what I do want to begin with, I'll show you that's where we are. I want to show you a little bit about where we've been. This talk is called the challenges of developing the UK's first hydrogen electric truck. Well, let's get into some of those challenges. So this is where we started from. So hopefully this looks a lot less slick to you than some of the images you saw earlier. These are our 4 mule builds that we designed when this is back to the summer of 2021. Now what you've got here is 4 different hydrogen fuel cells from 4 different suppliers, each requiring various levels of integration and integrated onto mule build platforms for testing. We started with a long list of more than 15 hydrogen fuel cell suppliers, got that down to 4 that were our top 4, and 3 out of the 4 suppliers even pre-issued these fuel cells to us, such was their desire to be considered for selection. I've also got another video showing them, very short video showing them in action at the Millbrook Proving Ground, which will be familiar to some of you on the call, I'm sure, just to show you how far we've come from these, what shall I say, hastily put together pieces of testing equipment to the glossy finished product we have now. So I don't think there's any sound on this one either for you, but this is just 3 of the 4 vehicles in action. And obviously, when we're testing hydrogen fuel cell vehicles like this, Chiefly, the thing first we need to do, we need to keep moving to keep running the battery down so we can work on that control software of switching the fuel cell off and on, as well as testing various fuel cell parameters like its efficiency, its performance under how quickly it takes to boot up and boot down again. Cooling performance is a big one. There was over 100 factors we scored the hydrogen fuel cells by before making our final selection for the finished product. And then fast forward over a year's time, we have our glossy integrated finished prototype, and this is what it can do. We did a drive from the Scottish border at Berwick-upon-Tweed. The left-hand side shows how far the battery electric vehicle made it just past Durham, right? It barely glimpsed, I don't think it quite glimpsed the Angel of the North on its way down. Our extra dual energy product made it to the ring of the M25. So we were hoping it would make it all the way back to our base in Essex, but 331 miles, pretty good going. We thought for a first run, and as you can see there, it was snowy, icy conditions. So we think on a warmer day we might have made it all the way back to our base in Tilbury. But you can clearly see here, I think what I hope it shows is the stark benefits of having the additional energy from the hydrogen fuel cell on the 7.5-ton vehicle. So, challenges of developing the UK's first hydrogen electric truck. Some of these points I've spoken about already, and hopefully some of it will serve as a summary, but some of it will be some new information as well. The first thing that we've encountered as being a problem, education regarding hydrogen safety. Now, it's fantastic to see people like yourselves are on this call, eager to find out more, because really, once you're educated about the risks of hydrogen, without trivializing them, it's all manageable. There are inherent properties of hydrogen. It's the lightest element in the universe. It makes it very difficult to contain, which people see as a problem because of the way it leaks. However, when used properly, this can be its greatest advantage. If you have a leak of hydrogen, if you don't encase it in a place where it can pool and concentrate, it will simply be buoyant and go away to the atmosphere. The same can't be said for diesel and diesel vapor, which forms harmful pools at floor level that are easy to ignite. We've constantly run into people who are concerned about having our vehicle inside at shows or even just having it on their side. And really just educating people and drivers about it is perhaps one of the biggest challenges we have. We also have the regulation landscape. So everything in the world of hydrogen is so new that we often run into struggles with lack of clarity in hydrogen in relevant regulations. I've named a couple there regarding the hydrogen exhaust content and the side impact tests, which are, is too detailed perhaps to get into now, but there's a lack of clarity in the regulations and there's no blueprint for doing any of this stuff. It really is cutting edge, and even the regulatory authorities aren't sure what the best answers are. And that feeds into the next point, which is a lack of hydrogen ready testing facilities. How can you run an EMC test on your vehicle if the vehicle can't use its hydrogen fuel cell indoors? It's an obvious and inherent problem. A lack of hydrogen supply shouldn't necessarily be a surprise to some of you on the call. The UK has an extremely limited number of hydrogen in refueling stations. At the last count, it had no less than 10. And sourcing small amounts of hydrogen for private use is difficult because you're dealing with massive energy companies that really don't see you as worth their time. And the good old-fashioned costs element of it as well. The costs of hydrogen prototype parts make development an extremely expensive endeavor, even if they are promised to come down with quantities later. So to get into the conclusions, what I want to talk about today, we have what we call the balancing act. And basically where we see it as 3 simple statements that form a balancer. A pure battery electric vehicle is a good solution, but it's not ideal for every truck duty cycle. There are numerous truck duty cycles which simply cannot be covered by a battery electric truck. Hydrogen fuel cell vehicles will be a reality, but for what vehicles and when will the TCO be optimized? For some vehicles, the TCO will be optimized faster than others, and that's what ultimately will drive for what vehicles and when. Current fuel cell and hydrogen costs make full hydrogen vehicles an expensive choice that are suitable for only the most extreme duty cycles. And this will change in time as well. We just don't know when. However, at the moment, what we at Teva are doing and what we believe we're doing, and what hopefully I've shown you a bit about today, is that dual energy provides the optimum balance of payload, TCO, and range for many customer duty cycles. And it's that balance that hopefully we're trying to achieve. Now, I believe hopefully there's some questions for me. But first of all, I just want to say thank you for listening. I hope you found it interesting. And if there are any questions that don't get answered or you don't want to ask right now, then I have my email is on the, I'll leave it on the screen for a little bit whilst maybe I answer some questions. Yeah, thank you.
Thank you so much. That was really fascinating. I mean, even I didn't know some of the things that you mentioned today, despite the fact that, you know, how we met and what we did and everything. So thank you for all of that. You did rightly guess, we do have a lot of questions that have come through as the talk was going on. I'll start with Nick Birkby's question. What is the UK hydrogen infrastructure like at the moment for fueling trucks?
Yeah, so hopefully I've touched on that one a tiny bit throughout the talk, but I'll say it again because the UK has about 10 refueling stations at the moment. Most of them are run by a company called Motive Fuels that used to be part of ITM Power. They've recently even taken the decision to close some of the stations they had initially opened a couple of years ago. And that's because they're pivoting away from, they initially set these stations up as being suitable for cars. They saw hydrogen potentially as a solution for cars. And in their statement closing some of the stations, they realized that potentially they made a miscalculation and that trucks and heavy duty vehicles is the way forward. So there are still a handful of stations that are open. There's a very good one in Birmingham. Air Products operate one at Heathrow Airport. That one was set up for the 2012 Olympics. But to be honest, we don't want our customers to have to rely on public infrastructure. And that's why I mentioned about the depot-based refueling, because we don't see it as something that can be relied upon. You go into other countries in Europe, in Germany in particular, and then in California in the US and the Far East in Asia, they have suitable public infrastructure that you could run a truck with no problem without any depot-based refueling. But in the UK, unfortunately, it's just not the reality of where we're at right now.
Big Foster. Will the vehicles be looking to use regenerative suspension along with braking as well?
Regenerative suspension. Now, that is an interesting one. That might be something I'll have to talk with some of my colleagues about. That's not something I would say I'm too familiar with, and I will say with some confidence is not on the vehicles right now. At the moment, the vehicles have just typical truck air suspension you would see on a typical truck like this. But perhaps that's something we should look into further, and I'll make a note of that.
Okay. JCB's direct injection hydrogen internal combustion engine isn't offered as a comparison. Is there a reason?
Yes, so hydrogen from combustion, it is interesting, and I understand why JCB have done it for their off-highway applications. Now, off-highway is interesting because you have massive transient power demands, and you also have, it's a much less suitable environment for a hydrogen fuel cell. Hydrogen fuel cells need a very pure airstream coming into them. It needs to be incredibly pure, and you can imagine on the dust of a building site is incredibly unsuitable for a hydrogen fuel cell. But also there's another factor. Whilst hydrogen, when used in combustion, has extremely limited carbon dioxide emissions, in terms of particulate matter and other emissions that people are concerned about in cities, it still produces a fairly considerable amount of those. So whilst it's in basically zero carbon, some of the other emissions that we're concerned about, I say like particulates, they are still a problem, which much less of a problem off highway. And so I think yeah, I could have offered it as a comparison, but it's almost as, in a way, it's almost as irrelevant as diesel, because there are some of the city emission zones would not accept a hydrogen combustion vehicle as being zero emission. Sorry, Ram, I really struggled to hear that one.
The question is, how much of the energy is recovered through regeneration? Is the question, I think.
Okay, yeah, regenerative braking, it's typically, it can be about 50% efficient. Yeah, it's about 50%.
Excuse me. Thanks, Dave. The next question is from April Bryan. It says, how does the safety of a hydrogen truck compare to that of a diesel or a BEV truck?
Yeah, so this is a really great question. Obviously, as I said, the safety points is something that come up a lot for us. And the thing about diesel trucks is people are very understanding of the risks involved in them, and they don't, people aren't scared of diesel trucks. It's a question of familiarity. The diesel isn't inherently a very flammable and explosive fuel. People often make the comparison, if you tried to conceive of a diesel truck now, it would never get approved. They would say, you want to put an explosive liquid inside a car and have me sit on it? That's ridiculous. Now, so basically what we have is a compressed fuel that has a fairly wide, we're talking about hydrogen, we have a compressed fuel that has a very wide ignition range. So it's about 4% to 75% mixture in air. So basically, our whole strategy regarding hydrogen, storing hydrogen on a vehicle, is to not create a situation where hydrogen can pool in a quantity where it can reach above the flammable ignition point. Now, we do that in numerous ways. The first thing is, obviously, we have the hydrogen is stored in compressed tanks with fittings that should be leak-free. Step one, as manufacturers should have no leaks in them. Next step, okay, what if it does start leaking? First of all, we have safety systems that can monitor the pressure of hydrogen in the tanks and the lines. If we see it's reducing over time, we know we have a leak, we know we have a problem. Third step, okay, it's leaking and you can't detect the leak. Then what we do, we design the truck in a way where there are no local maximums, which is what we refer to as any point where hydrogen could pool, and then you have a significant problem because you have a flammable mixture. Hydrogen is so much more buoyant than air that if you give it any route to escape, it can easily escape out and above the cylinders. Basically, that's the core safety premise. It's actually easier to do in a truck than it is in a car, because in a car, the hydrogen tanks are below the floor level of the car. We've had Toyota Mirais. There's been 50,000 of them on the roads for years, since about 2015. This isn't quite as new technology as people think. And that's before we even get into things like the thermally activated pressure relief devices on the tanks. But basically, I think what I'm trying to say, because I could talk about the safety of these vehicles for a very long time, is that there are in some inherent dangers, but like all dangers, they shouldn't be trivialized, but they can be managed. And people shouldn't be scared of driving a hydrogen vehicle. Similar to problems like thermal runaway with battery vehicles, which I think was part of the question as well. These are problems that are inherent and need to be managed, but they're not something necessary to be scared of, and they aren't really any more dangerous than diesel, I would say. Sorry, Ram, again, I missed the first part of that question. I think you might have to lean a bit closer or something.
We basically asked you maybe 4 questions, and any others that I'm not able to ask you because of time today, I'll email them to you if it's okay with you.
Sure.
Okay. So the next question we have is from Dave Terry. What is the periodic service requirement for the fuel cell? Or how often is a service or replacement required, and what does it cost?
Yeah, so that's a really great question. I think I mentioned a second ago that hydrogen fuel cells, they are quite a sensitive piece of equipment. So they're probably more at home in a lab inherently than they are on a vehicle. In terms of serviceable parts, though, it's actually quite simple. It's actually quite few. In terms of the fuel cell itself, you have its air induction system. That's a simple filter that will need to be replaced once a year, probably, depending on where you use it. Again, I say if you use it near a building site, you might need to replace it more often than if you're using it in an area of extremely low pollutants. On the hydrogen side, the hydrogen storage systems, they don't really have any maintainable items. They often have a coalescing filter that should be checked once a year. But other than that, they're designed to be a sealed system and with no real maintenance items other than periodic leak checks, which could be done on an annual basis as well. And then for the hydrogen fuel cell itself, it also has in its cooling loop, it has a deionizing filter, which reduces the electrical conductivity of the hydrogen fuel cell's coolant loop. That should be replaced about once a year. And it also has a particulate filter in that coolant loop as well, which again, you could replace on an annual basis. It's actually a process we've done quite recently, developing the after sales arrangements for these vehicles. And we've actually got everything. The after sales people were pleasantly surprised, I would say, about the simplicity and the periods for these checks and how, and what we expect is all of these will get longer as time goes on and we have more confidence in this technology.
Thanks, Tej. The next question I have is from Thomas Sharples. It's about how do you balance the fuel efficiency of using hydrogen versus the weight, because storing hydrogen can be heavy, and how does it impact your potential range? And is there an optimal fuel tank size?
Yeah, so again, this is a great question. And I think how we've done here is we've started with a battery that is easy to charge in 5 hours. And that's our starting point, because it means you can recharge the battery in between shifts without an issue with just a 22 kilowatt charger. So we start with 80 kilowatt hours of energy from a battery. And then the way we've sized the dual energy product is we're targeting that 435 kilometers of range that comes from our customers. And then we go backwards from there. We start with the 80 kilowatt hours of battery energy, and we add the required hydrogen to get us to 435 kilometers on a given customer drive cycle, and a half payload is how we typically run our range calculations. So we get to a point of having this vehicle that is easy to charge overnight and has a range of about 100 kilometers on battery only, and then the rest is done by the hydrogen tanks. And we're applying the same process to our 19-ton vehicle. So that will have more hydrogen cylinders in order to achieve this extended range. But we're still going with that same principle. And the thing to remember is that the hydrogen is much more by weight is a much more efficient way of storing energy. So once you want to take big payloads a long distance, you need to have the hydrogen. It's about having that balance of where you can still charge it easily and have the cheap electricity to charge you up and take you some distance.
Thanks, Tej. We'll do 2 more questions now in the live session, and I'll send the others to Tej in an email. The next question we have is from Andrew Mitonet. We see a typical degradation of 15 to 20% in battery energy capacity over their lifetime. What does the degradation look like on a fuel cell?
Yeah, it's another great question. So before the fuel cell goes from beginning of life to end of life, we describe end of life as not necessarily being defined by loaded time like you do for a battery. For a fuel cell, the thing that causes degradation in it is actually going from powered on to powered off. So from a low power mode to a high power mode, or a high power mode to off. And we can minimize this with our range extender. So that's another benefit we have actually of using the fuel cell as a range extender. But to put some numbers on it, the fuel cell drops in efficiency in terms of hydrogen consumption by around about a 10%. And in terms of its ability to reach its maximum power, that also drops by about 10%. So we see our 50 kilowatt fuel cell at its end of life, it can only produce 45 kilowatts. And as I say, obviously that's about a 10% reduction. But it's something that we can hopefully stop ourselves ever getting to that end of life before, and so we don't have to worry about it.
Thanks, Tej. The final question for the evening that I'm going to share with you is from Chris Griffiths. And I think he shares a common sentiment with all of us when he says, great presentation, excellently presented, well done. And now the question is, what was the most challenging type approval system test to go through?
Okay, so first of all, the battery electric vehicle is the one that's been type approved. Some of the challenges I think with the hydrogen vehicle are still to come. However, I think the answer will be the same, and that's EMC. So electromagnetic compatibility. For an electric vehicle, it is incredibly tough to pass that test. You have so many electrical devices on the truck interfering with each other, and even identifying the sources of the problems during testing can be incredibly difficult. And I think it's obviously a very important regulation. For those of you who don't know, issues with EMC, it can cause interference with pacemakers and other vehicle systems. So obviously it's a very important regulation to pass, but with an electric vehicle, and especially if you add a hydrogen fuel cell to the mix as well, can be incredibly difficult. And I think it has been a big challenge on the battery electric vehicle, and I think it will be a big challenge on the hydrogen fuel cell vehicle as well.
Thanks, Tej. I will.
Okay, right. Well, Tej, that was a very
Division Northwest.
Right, thank you. That was a very interesting lecture that you delivered. I found it very, very interesting. I was very impressed with the progress you have made since the onset, and your foresight for the future, which is obviously very good. The way you have balanced the proportion of hydrogen and electric power use is very impressive. And given your scope for the future, when the cost of hydrogen comes down lower, then obviously you can make changes to cater for that. In general, it was a very, very interesting lecture. I think you presented it extremely well, and thank you very much for doing so. Normally, when we have face-to-face lectures, we would all give a round of applause. So even though you can't hear it, can we give you a round of applause? And thank you very much for that. Now, as a little thank you for delivering this lecture, we are going to send you a little gift, which is a working model of a Stirling engine, which I'm sure you and your family will find extremely interesting and fascinating, and that will come through the post. Okay, so thank you for that. Ram will send you an email just to formally thank you from the institution, and that really brings us virtually to the end of the session. I would just like to say a few words about the next lecture, which is going to be on the 4th of April, and it is on a very appropriate subject, carbon capture and storage. So I think that should be a very interesting lecture. I hope that all those that have come to see this lecture will join that one. And I think all that's left for me is to thank everyone for attending. Enjoy the remainder of the evening, and thank you very much. Okay, that brings us to the end. Thank you. All right.
Hello, everybody.
Thank you very much, David. Thank you, Ram. Thank you, everyone, for listening. Very appreciate it.
Thank you. That was very, very excellent. I enjoyed that. Okay. Bye-bye, everyone. Bye.